Hi everybody, my name is Greg Hancock, and along with my highly discriminating friend Patrick Curran, we make up Quantitude. We're a podcast dedicated to all things quantitative, ranging from the relevant to the completely irrelevant. In today's episode, we provide an introduction to the item response theory model, what it is, how it relates to traditional factor analysis, and how this modern approach improves upon some of the limitations of classical test theory. Along the way, we also mention weinerness, memorizing Latin for punishment, eggszample, in other words, ITR, switching A and B, I'm not defensive, you are, why biostatisticians hate us, page 3, subsection 8, binary babble, EAPs and MAPs, computer adaptive testing on the playground, Bob's your uncle, and the liberal arts mic drop. We hope you enjoyed today's episode.
What does it reflect on me if I start a story by saying I was not trying to be a wiener?
That you know everybody around you instantly assumes that you're a wiener.
Now, the irony is, in this particular case, I was trying to be a wiener.
Okay.
But I just need to establish that there is some wiener domain that evidently I have some control over. In this rare instance, I actually was trying to be a wiener.
Okay.
Now, I say rare because people infer wienerness about me when I sometimes ask a question or make a comment, and it is completely misplaced. And I say, no, that was an honest question. I really wanted to know that. In this case, I was indeed trying to be a wiener. And for the record, I think I succeeded. Very briefly, I was in a talk a while ago, and it was a very technical talk. A student very bravely asked a question. And I say bravely because the presenter had a bit of an edge to them and they were very clearly flexing in front of the mirror with their math chops. I was very impressed with the student. The guy responded being a wiener because I think he had no control over it. And he answered in a very curt way. And the student asked for a clarification, and he drew up this very complicated equation on the board, and in this mic drop kind of voice said, Q.E.D. And there's just silence. And I raised my hand, and this is when I flipped the wiener switch on. And I asked a question that not only was he unable to answer, but he crossed his arms and glared at me. I said, I have a follow-up question. And he said, yes. And I said, can you please tell us what Q.E.D. stands for?
That's a supreme wiener moment.
You know, I'm on a continuum of wienerness, and I have to admit that I really shone that day. You're math guy. Would you please tell me what Q.E.D. stands for?
Wait a minute. I'm not Latin guy. All right. It's not something I use every day, nor would it be my mic drop, but it's something like quod erat demonstratum or something.
That is exactly right.
Okay.
I had a middle school English teacher mom. I was grounded half of my adolescence. As punishment, I had to learn Latin phrases and memorize them and give them back. All right, how do you take a child who's kindling a flame of curiosity and beat it out with a wet towel? It is, as punishment, assign them to memorize Latin phrases. 50 years later, I still remember the majority of them, which, okay, Mom, you get an atta girl for that one. But that is exactly right. And the literal interpretation is approximately what was to be demonstrated.
Okay.
It's a very common math stat term. You go through a proof and then you put Q.E.D., and it is like this self-righteous mic drop in print of, there, I told you so. I just do find it funny, and I am as guilty of this as anybody. We use these Latin acronyms all the time without knowing what they stand for.
It's true. We're forced to, right? The conventions that we use for writing assume that we know what they mean, how to use them properly, and all of this. And I'm not sure I do. I certainly know the manuscripts I review, people don't really know what they're doing.
As I said, I am not casting stones living in a glass house. I know the IE EG distinction. All right, do you know how I remember this? All right, anybody who's listening, as opposed to those who are not listening and wouldn't have heard me say that, we'll set that aside for now. It was kind of like I was talking to somebody the other day, and I said, I was talking to my dad before he died. And I was like, did you really need to clarify that? Couldn't you have just said I was talking to my dad? But anyway, think to yourself, what is the proper usage of EG versus IE? Mm-hmm. Well, I do know the difference, but only because EG, if you pronounce it, it's egg, and it's like example. And IE is kind of like in other words. And so it's example and in other words. Technically, it is exempli gratia, meaning for example.
Okay.
And id est, which means that is. Now, in fairness to me, you will forever remember EG as example.
I don't have to because, damn it, my parents bought the same wiring at the hardware store for me. That is exactly how I remember it. Example.
Really?
I swear to God.
Because we didn't talk about this beforehand.
No, we did not. Now, the other one, i.e., what is it?
In other words.
In other... Yeah, so I always thought about that as is equivalent. I know that's not what it stands for, but I actually made it an acronym for something else in English. But I like yours better. I will forever call it in other words. Thank you. That's super helpful.
Now, one of my favorites, because folks, if you want to be a wiener in writing, like, I mean, a real wiener, but not seem it because you're using Latin, my favorite is sic, S-I-C.
Yeah.
And it's actually not short. That is just a Latin phrase, and it means thus or so. But what you do is if there's a grammatical error or a typographical error in an original quotation, you put bracket SIC, which is, hey guys, this isn't my fault. It's them.
That's right.
And so that's like wienerdom in Latin.
That's Latin for I'm way smarter than the author because I can correct their grammar.
Right. Do you have a favorite one?
I don't have a favorite one. I have a least favorite one, and my least favorite one is CF. Do you ever use CF?
I was taught incorrectly that stood for cited from, which is not only incorrect, but it doesn't even relate to what the abbreviation is.
All I know is I can't use it properly. I just don't know if it means that you use CF to provide some source that has a different viewpoint where you're saying you should compare this because there are other ways of looking at it, or if it's just essentially providing more information on the thing. I don't know how to use it, so I just don't use it. But it seems like I'm a grown-up and I should know, but I don't know how to use it.
You probably should. I'm just saying.
Thank you. Wiener.
What is that in Latin? You're always on Google. Look up wiener, and it's probably like wienerus enormi or something.
It is Patrick.
Damn Google Translate.
Yeah.
CF that I was later taught was compare to. Uh-huh. How I use it, which may well be incorrect, you would give a citation or a perspective and then say paren CF, and it's kind of like, but compare to this. So I use it as a different perspective.
Okay.
But I may well be wrong. There's, again, an English lit major yelling at their steering wheel right now.
Listening to our podcast.
Yeah. You've made certain life choices that have not been ideal. But it is funny in academia because it's not just related to the IEEG. And then we can get into a whole bunch of the, oh, well, it's a non sequitur. I mean, you can drop these in left and right, although I do like that one. A non sequitur has been applied to me by you repeatedly. Anyway.
Speaking of Latin, you're going on ad nauseum.
We're eyeballs deep, not only in the acronyms in our field of SEM and CFA and EFA and all these things, but there are some that almost have become proper nouns. And recently, I had a student express surprise to me that IRT actually stood for something.
I should not point the finger at this student because in graduate school, I received zero training in IRT. None. To the point where the other grad student, my very good friend Keith Teedy, and I, when we graduated, we said just as a joke, "Oh yeah, we know a lot about ITR." We didn't know what the hell it was.
Our goal here today is to convince you that IRT actually stands for item response theory. And we just want to chat a little bit about what is IRT, how is it similar and different from factor analysis. Like everything, there's a really interesting historical line in the development of how it came to be, just so that if you're at a cocktail party, you don't say, "Oh, I did an ERT model with my data."
You said something that I really want to underscore here, and that has to do with the fact that it is similar to other things much more than it's different from other things. And we have a habit in the courses that we teach or the ways that we learn as graduate students, we have a habit of compartmentalizing things and thinking about them much more as separate. And it is the case that certain things arose under different historical contexts, but in the end, there's so much similarity that I think that's much more useful to try to frame these things. IRT is very much related to things that people out there already know, even if they haven't been exposed to it. So I hope we can make some connections for people.
To objectively reflect that the IRT model is very similar to the factor analytic model, one of the titans in the field in the development of factor analysis was L.L. Thurstone, who many people identify as the first formulation of the IRT model, and this goes back to 1925.
Now, if I'm being completely honest, I think you're a little bit biased in favor of Thurstone because you walk the hallowed hallways of the L.L. Thurstone lab. You have held in your hands the chalkboard globe that he had to do a lot of factor analysis rotation. That said, I think historically you're right, that his fingerprints are all over this stuff.
There are many entry points into this conversation, and indeed in all the 5 minutes we spent organizing before turning on the recorder, we talked about multiple of them, but did not decide which one to use. So I'm just going to throw to you. A couple of episodes ago, we talked about classical test theory, and that did a lot of things that we liked, but it actually imposed a lot of things we kind of didn't like.
You're pop quizzing me, aren't you?
It's less of a pop quiz and more we didn't make a decision how to pivot.
Okay.
And the way I did the throw is now you're going to have to decide.
Okay. I got this. Well, one of the things that we did with classical test theory when we explained it is we actually explained it with some framing around it that is much more a latent variable framing, even though it has its origins in true score theory, right? We tried to frame it as a latent variable method, which does, I think, make the connection between classical test theory and item response theory a little bit clearer. But let me tell you one of the big things about classical test theory that just kind of leaves you hanging. There are a bunch of limitations of it. We talked about assumptions that people typically make last time about like parallel forms, other things, and some of them are testable, some of them are not. One of the main limitations of classical test theory, though, is imagine that you have a number of test items, and so you go out and you get a sample of individuals, and then you ask a question like, ooh, is that a very hard test item right there? Or what are the ability levels of the people who have taken your test, right? You might have certain questions like that. The problem with classical test theory is that it is entirely dependent upon the sample of individuals that you have. Whether you are assessing how difficult an item is, right? Well, how difficult is that item? Well, that depends. Did I get a bunch of smart people in my sample or not? How reliable is this particular instrument? Well, that depends very much on the sample of individuals that I have. So if I were making up a wish list, what I would really like to have is a method that, to the best of its ability, could transcend the sample that I have in my hand and give me an assessment of the items that I have on my instrument, maybe of the people that I have in terms of what their abilities might be, and some other characteristics as well. But again, transcending the sample that I have in my hand. That would be a wish list for me.
This is one of the biggest limitations of classical test theory and coefficient alpha. It drives me crazy when you read paper after paper after paper where someone says we're using the XYZ scale that has proven reliability and then cite a publication from 1982.
Right.
First, that was 42 years ago. Second, That was a reliability that was based on the characteristics of the sample in 1982.
That's right.
What we want is to think about our items as a random sample from a universe of items, and that the understanding that we develop about the measurement properties and what we're going to call test information instead of reliability is not generalizing to the sample at hand, but generalizing to the set of items and beyond. And that seems like window dressing, but it's really, really not.
I did already mention that I didn't have any training in this. The funny thing was when I had to give my first job teaching talk, right? You almost always have to give a job research talk. At some institutions, they want you to give a teaching talk. The first job teaching talk that I had to do, they asked me to do it on IRT. And I'm like, oh, dear God, of all the topics they could have picked, they're asking me to teach on ITR. When I came to Maryland a number of years ago, and this was not a job talk for the University of Maryland, one of our senior faculty here at the time was a guy named Chan Dayton. And Chan has had a hand in a lot of early latent class analysis kind of work, did a lot of really good stuff. But he was telling me a story about when a guy named Ben Wright came to the University of Maryland just to visit. And Ben Wright was somebody who was very active in promoting some aspects of item response theory in the 1960s, 1970s, and on. What he did as a demonstration was he took a whole bunch of data and he grabbed some folks from the upper end of the distribution. He grabbed some folks from the lower end of the distribution. He grabbed some folks who sort of spanned the whole ability continuum. And he went through and did this thing called IRT. Specifically, he was doing something called Roche modeling, which is related to item response theory. And he fit these models, which we'll talk about, but he got about the same estimate of how difficult the items themselves were, irrespective of which sample was chosen. And the faculty here at Maryland, they were looking at this going, oh, damn, because all of the classical test theory that so many people had been doing for so long, this seemed to overcome that limitation. So it is a huge sell.
If you know traditional factor analysis, you actually already know item response theory. We've just got to put a couple of wrinkles on it. And those minor wrinkles took like half a century to figure out. So I may be minimizing that a bit. But what I mean is, let's think about a classical factor model. So we have 20 items. We're going to assume that they're approximately continuously distributed and, for simplicity, approximately normally distributed. Mm-hmm. And the whole factor model is we observed a set of correlations among those items, and that we believe that a large part, if not all of those relations, are due to an underlying common cause that we call a common factor. And when we estimate that factor and remove its influence and look at what's left over in the item, that's called local independence, is that the residuals are no longer correlated with one another because we estimated and removed the shared common cause. That literally is the cornerstone of the item response theory model, except we have the drunken poke in the eye that our items are discrete. Often they're binary, so correct, incorrect, true, false, present, absent, but they might be trichotomous, they might be ordinal. What it is it's very, very similar to, we can use a multiple regression model with a continuous outcome, but when that outcome is no longer continuous and we have to embrace that they're discrete categories, we can no longer use the regression model. We have to move to maybe a logistic regression model, and that is the item response theory model. So picture in your mind's eye a 25-item math test that, just for simplicity, we either have correct or incorrect, all right? So they're just binary outcomes, 25 items. We have a contingency table, and we can see that there are relations among these items and whether you correctly endorse them or not, and we can say, oh, I think those relations can be in part attributed to an underlying math ability factor. And for people who are higher on this underlying factor, they are more likely to get items correct. People who are lower on the continuum are less likely. if you're driving, keep your hands at 10 and 2 on the steering wheel. We want to be safe here. Picture an XY axis. On the x-axis is the ability factor. All right. Now, where does that come from? How do we get that? Well, we'll talk about that in a minute. It's latent and we didn't observe it and we have to infer its existence. Underlying ability is on a continuum and we'll go ahead and assume that's normally distributed. So picture a really nice univariate normal distribution of ability on the x-axis. On the y-axis is one math item. It's either correct or it's incorrect. Well, as we move across the continuum on ability, we can actually map out this beautiful logistic curve. It's kind of a squished S, and that is the probability of endorsing the item correctly. So we can write a mathematical expression of what is the probability of correctly endorsing a particular item given individual variability on the underlying math ability continuum. In our continuing quest to just mess with you, when we were all in middle school, we learned that a line was A plus BX, where A was the intercept and B was the slope. Mm-hmm. We're going to go ahead and flip that in the IRT.
No.
And there's no reason other than just screwing with you.
No. Go back and slap somebody.
There's wienerdom. Again, wienerus and normi is we're going to flip those just because we can. Typically, the intercept is going to be represented by B, and it's really cool. That is literally at what level of the underlying ability continuum do you have a 50-50 chance of endorsing the item correctly? That is the intercept term. That is sometimes in education called the difficulty parameter, or in psychology, the severity parameter. Because think about it, higher levels of that parameter mean you've got to have more of the underlying construct to endorse that correctly. That's why it's called difficulty. Higher levels are more difficult items, lower levels are less difficult items. Now, it's a curve, so it doesn't have one slope, right? Because that's going to be the linear slope of a tangent line that changes across the entire life of the curve. And so what we do is to say, what is the slope of the tangent line in the middle of the curve? What is that steepest slope? And that's called discrimination. And if you think about it, that is if you have a 1 unit change on the underlying theta, which is your ability, what is your change in the probability of endorsing that item correctly? The flatter that is, the less discriminating it is, right? If you're low on theta, you got about as much of a chance as if you're higher on theta. But the steeper that is it's more and more discriminating. That's for one item. Now just picture a plot that has 10 of those curves, and those are item characteristic curves for a 10-item test.
Which one is the difficulty again? Parameter.
Come on. Aren't you like the chair of your department in the School of Education?
It just means I can make other people know these things.
B is the intercept.
The B is the intercept. Yeah. So the B is the difficulty parameter here. If you think about this S curve that you can sort of change the shape of, you can squish it to the right, and that means that it's a more difficult item because in order to have 50% get it right, you have to have a very high ability. We would call that a difficult item. You would call that a more severe item, right?
That's right. If we were doing psychopathology, you would have to be higher on latent depression before you endorsed that symptom. So it's a more severe symptom.
Good. So the S curve can be shifted left and right, but then as you said, it can also be steeper. And the steepness of that tells us something about, honestly, whether or not that's a very good item. An ideal test item in our world is one that really helps to tell the difference between people who know their stuff and people who don't know their stuff. If you have a really steep tangent of that line that you're putting through right at that point of inflection of that S-shaped curve, then that means that item is doing a really, really sharp job at telling the difference between folks who are lower and folks that are higher. But the flatter that is, then it's like, people get it right if they don't know a whole lot. People get it right if they do know it a whole lot. In your world, that would I'm guessing mean that that's not a very useful symptom to help diagnose that underlying condition. Is that accurate?
That's right, because it's weakly related to the underlying trait that you're interested in. I mean, if you think about it logically, is what that means is that people are responding to it almost independent of their underlying trait. So it's not telling us anything about the trait itself, right? Always be selfish in these models. And we ask ourselves, is this item giving me information to help me understand the estimation of this underlying trait? If it's only weakly related, no, it's not a good item.
So now I want to go back to something that you ever so conveniently slid under the carpet, because one way to view just about everything you said, you just elaborated upon a logistic regression, right? And we've talked about logistic regression before. So let's go back to that x-axis that you mentioned. When we're in the logistic regression world, that x-axis is just some measured variable that we are telling ourselves is continuous. But turns out we can't see what's on the x-axis here. Am I right?
You just nicely described the entire factor analysis model. Okay. The one that you use. I'm not defensive, you are. That's the fun part, and this is why biostatisticians hate us. Okay, it's on the list of why biostatisticians hate us.
Sure, it's a long list.
Here it is. Go to your page 3. It's about halfway down there.
Subsection 8.
Which is, we're doing a logistic regression where we're missing the predictor for all observations. Mm-hmm. But that is what a latent factor is. We believe it to exist. We did not directly observe it, and we're going to infer its existence based on what we did observe. It is exactly the same as an exploratory factor analysis, or as a confirmatory factor analysis, or as a latent curve model, or any of these kinds of applications. It's just here, if you have binary outcome, all you have is a rectangle of zeros and ones. Mm-hmm. You have nothing else. And from that, we want to extract all of that information.
It's brilliant. It's incredibly clever. And relating it to factor analysis, to me, actually makes a lot of sense. In factor analysis, if you wrote out every observed variable as a linear function of an underlying latent predictor, you'd look at each of those simple regression equations and you go, well, I can't solve for the slope of that because nobody has a score on the predictor, which is a factor. But we use the pattern of correlations that we have to say, yeah. But we know how that factor would have to relate to item 1 or variable 1 and variable 2 and variable 3 and variable 4 in order to give rise to this pattern of correlations. Now we switch the information a little bit and we say, okay, well, what characteristics would item 1, item 2, item 3, item 4 have to have even though the predictor is latent? In other words, what discrimination and what difficulty would each of these items have to have in order for the data that we observed, which is now a whole bunch of zeros and ones, to have the maximum likelihood of occurring? So like in factor analysis, it's like we're kind of estimating around the latent thing to figure out what the implication of the model would have to be for the type of data that we have. It's very clever.
And it makes your mind bend a little bit because in a linear factor analysis, the covariance matrix are sufficient statistics. You can define the IRT. Sufficient statistics are weighted response patterns. So imagine that you have 10 items. There are 2 to the 10th possible combinations of those. Now, you would never have that many in a discrete sample, but those are the possibility. But let's say 8 people had 011, 0011, 001. All right. Mm-hmm. That pattern, which I can't repeat because I just made up, whatever that pattern was, you put 01100, whatever, a space, and then 8, because 8 people had that response pattern. And then you do the next one and you do the next one. Those are actually sufficient data to then build that likelihood that you alluded to. What are the values of A and B for each item that maximizes the likelihood that you would have observed those patterns of zeros and ones? And it just scales up and down from there. It's absolutely fascinating.
It's beautiful, right? Because there is a probability associated with any given pattern of responses. So whatever you said, 0110110, whatever your binary babble was there, there's a certain probability associated with the response to the first item, response to the second item, response to the third item. And each of those probabilities is a function of the characteristics of the item, which in the two-parameter logistic model that you're describing include discrimination and difficulty, but also conditional upon the ability level that a person has, because the probability of getting an item right is going to be much higher for someone with higher ability and much lower for someone with lower ability. So in the end, we have probabilities of responses to each of these that are conditional upon the ability of the individuals and rest on that assumption that you mentioned earlier about conditional independence. That is, that once we take the latent variable into account, the ability level, whatever you want to call it, then the responses to items 1, 2, 3, 4, 5, 6 are all independent, right? They're conditionally independent. And that's how, in pretty much every maximum likelihood application, we can just multiply the isolated probabilities next to each other to get the probability of the data that we observe across all of those. So in this maximum likelihood process, we're estimating the characteristics of the item, but something we're also interested in this world, much more often than factor analysis, we often want to know the ability level or the factor value that people have.
You're exactly right. Think about the different uses of factor analysis in general. One is understanding the psychometric structure of a test. What are the loadings, right? In a linear model, we have factor loadings. We might have item intercepts. We have item residuals that we can translate into communality estimates, which, just to confuse you, is another word for R squared. Are there multiple factors? Do factors correlate with one another? To what magnitude do they correlate? These are all kind of things that we want to understand the structure of the test. Often, what will be done more in an educational setting than, say, a psychology setting is you use these kind of results and the item parameters to select good items. So as Greg alluded to, if you have an item characteristic curve that has a really flat slope that's not very discriminating, well, maybe it's not a good item, so we say, toss it.
Yep.
We're not doing an a priori test of theory. We're trying to come up with a reliable, valid assessment of math ability, and that's not a good item. Drop it. We might also want to select items, and Greg also alluded to this. We don't want all the difficulty parameters clustered all together, where only the kids who are above the mean of theta have any chance of getting these items right. So we select items to be fanned out across the continuum of theta. So one is understand the structure. One is to understand developing an item pool that has this coverage in ways that we want. But what Greg is saying is it's not absent in linear factor analysis, but less present. I don't know, can I say that? Which is getting scores on theta. And these are factor scores. Theta is an underlying latent variable that we didn't observe, but we can use information about the set of binary indicators if we're working with a binary outcome model. There are two big ways. There are many ways. Again, in the acronym soup, they're called EAPs and MAPs. And an EAP is an expected a posteriori, and a MAP is a maximum a posteriori. And they correspond to factor score estimates within the linear factor model.
And in the education world or the assessment world that I tend to come from, we like to get these estimates, sometimes referred to as theta estimates, because theta is very commonly used as the symbol that represents the factor or the latent characteristic that we care about. For example, math achievement, we not only want to get the characteristics of the items, we also want to get some information about the individual that, oh, this person, if we think about it on a z-score scale, for example, this person's theta estimate is 2, right? Well, in a z-score metric, that means that that person is estimated to be 2 standard deviations above the mean on math achievement or whatever it is you're doing. Or this person's theta estimate is a -1. Okay, that person is 1 standard deviation below the mean on math achievement or whatever it is you are assessing. Almost always in the assessment world, we want to get these estimates, and Patrick mentioned a couple of ways to try to get those out, EAPs and MAPs. One of the things that you had mentioned that if we are designing an instrument, whether it's an assessment instrument in an educational setting or achievement setting, or it's a diagnostic instrument within a psychological or psychiatric setting, that we often like to have items that sort of span the difficulty continuum, right? We've got some easier items, we've got some harder items. And the main reason is that we don't know who the people are that we have, right? If they're going to have a harder time with these items, have a harder time with those items. So we like to have items that span the continuum of where we expect people to fall as well. And one of the cool things about item response theory is that there's a concerted effort to come up with a continuum where we can at least think about both people and items falling. And we can think about it as a z-score continuum as you want, because like Patrick had described, there's that x-axis. Imagine that that's in a standardized metric. If someone has a higher ability, they're more to the right side. And if someone has a lower ability, they're more to the left side. If an item is harder, it's more to the right side. Or if an item is easier, it's more to the left side. People and items can be thought of as being closer to each other or farther apart. If there's a lot of gap between where someone falls on that continuum and the difficulty of a particular item, then that means we're going to have an easier time knowing how that person is going to perform on that item. If that person is really high on the continuum and the item is way down on the left side, we'd say, oh, you're totally going to get that right, because your ability level is way higher than the difficulty level of that item. On the other hand, if a person has a lower ability, but the item is very, very difficult up on the right-hand side, we go, sorry, man, there's just no shot you are going to get that one, because the item is so much harder relative to your ability level. But that also means as the difficulty of items and the ability of individuals get closer, then it's a lot harder to know how well that person is going to do on that particular item. So if I wanted to gather a lot of information about an individual, if I've got a really smart person like Patrick, I'm not going to give Patrick a whole bunch of easy items to try to understand something about Patrick. If I really want to fine-tune my understanding of Patrick's ability, I want to give him a bunch of items that are really close to the area where I'm estimating his ability to be. So one of the really cool things about item response theory in general is this notion of a single continuum for both ability and items, and then ultimately the ability to pick and choose items to try to tailor the information that we get around individuals to get a more and more refined understanding of their ability.
I think I related on an early episode about how a bunch of fifth graders on the playground organically discovered computer adaptive testing when my kids were in middle school, because they had standardized testing, they had breakout on the playground, and they were asking each other about what did you put for this or that. Within a minute, they figured out that they had gotten different items because somebody was like, I didn't get that. Nobody asked me that. And each of them kind of knew who was better at math and not. And at the dining room table that night, my daughter said, I kind of feel like the computer was giving the smarter kids harder items. And I was like, an 11-year-old just invented computer adaptive testing. This is where you either find it really, really cool or mind-numbingly vexing, or like me, maybe both. Let's say there's a 50-item test. Let's say there's not computer adaptive testing. I get 50 items and Greg gets 50 items, and we each got 40 right. We each get 80%. Obviously, we have exactly the same score. But maybe I get a z-scaled IRT score of 1.5, and Greg got one of 2.1. So I'm 1.5 standard deviations above the mean, but Greg is 2.1 standard deviations above the mean. But this is non-American. I got 40 right and you got 40 right. Well, one of the beauties is, and this is one of the phrases I love with IRT, it's not just how many items you got right, it is which items you got right. So the items that Greg got right were characterized by different discrimination parameters compared to the items that I got right, and these differences are then reflected in differences in our individual score estimates. But this is a hallmark feature of IRT scoring, is these are upweighted and downweighted relative to the item parameters. This is particularly useful in psychology research because if you just take account where you equally weight, sometimes I feel lonely even when I'm around other people, and I often fantasize about harming myself. An IRT model is likely going to differentially weight those items based on differences in the associated item-specific parameters, and in particular, the discrimination parameters.
It's brilliant. It's fascinating. It's also very frustrating. Imagine it in an achievement setting where you have to explain to the parents that, yeah, we know that your kid got the same number right as the other one, but that kid gets a higher score. It's a very difficult thing to explain to your constituents, but it makes complete sense. And it really telegraphs the thing that Patrick said was invented there on the 5th grade playground. In fact, if we had full license, there's no reason we have to go to 50 items. I give an item that has a difficulty that's 50-50. And Patrick gets it right. And I go, oh, okay, I think, well, his ability is probably on the positive side. I'm not giving him an easier item. I'm going to give him a harder item. Does he get this one right? Ooh, I think his ability is even higher. You could imagine these adaptive frameworks. And of course, the technology exists for all of this, where it can actually take only a few items before you have homed right in on where a person falls on the ability continuum. Now, you've gotten less information about items because you haven't administered all the items, but as far as an assessment of where an individual falls along the continuum, you can do it in very few items if you have a nice big item pool to be able to choose from. It's very clever.
It is, and you're mischaracterizing my test taking, because every standardized test I've ever taken, the items inexplicably get easier as I go. So I didn't understand that until now. That makes a lot of sense.
Okay.
Could I have permission to drunkenly punch you in the face?
Oh, please.
Let's say now that I got 40 items right and Greg got 40 items right, and they were exactly the same items right, but we still don't have the same score. Well, why is that? Because there's a thing called differential item functioning. And that is measurement invariance. Does that A and B parameter for a given item hold across biological sex, across racial group, across first generation status, across rural versus urban, whatever we might be interested in? But Greg and I may have gotten exactly the same items correct, but Greg has an individual characteristic that upweights his a little bit because those item parameters are different in our two subgroups. So everything that we talk about, measurement invariance, complete invariance, partial invariance, everything in the factor model, exactly the same thing holds here, but it's referred to as differential item functioning. And I always hated that phrase until I realized, oh, it represents differential item functions, as opposed to this ridiculous failing to support partial invariance that we have in factor analysis. Is there one B parameter for item 3, or are there two B parameters? And then if you want to MNLFA it, right, that is the genesis of the moderated nonlinear factor analytic model of Bauer.
That's right.
That's the nonlinear part of the factor model, is we have the full access to the MNLFA, where we can have multiple covariates and run it up and down a continuum of a covariate if we are so inclined.
So then it's not just 2B or not 2B.
Ooh, we're almost out of time.
Oh, come on. You and I have been describing this mainly as what we've referred to as a 2PL, a two-parameter logistic model. There are lots of different flavors of item response theory models. There's a 1PL, one-parameter logistic model, where we assume the discrimination level is the same for all of the items. And why would we do that? I don't know, because maybe we have chosen items to have those characteristics, but that the items just differ in terms of difficulty. It's a simpler model, but actually to be able to meet that assumption, there's probably a lot more work on the front end. And, oh, by the way, it's a testable assumption. But then there's also a 3PL, a three-parameter logistic model, where we have an additional parameter, sometimes referred to as a pseudo-guessing parameter. If you have 5-option multiple choice, you're going to get items that you know absolutely nothing about, where you just have to randomly guess. You're probably going to get those right about 1 in 5 times, right? And so the baseline isn't really 0 for your performance on things. Your baseline is somewhere else. So we can retweak that logistic function so it's not asymptoting out at the lower end of 0, but maybe it's asymptoting out at 0.2 or some other meaningful thing. But there are lots of other models too.
And they all share these common themes of moving along the underlying continuum, and either you're moving from a 0 to a 1 in a binary, or you have an ordinal and you're moving from a 0 to a 1 or a 1 to a 2 or a 2 to the 3, and that's the equivalent of cumulative logit. Whatever they are, they're trying to achieve the same thing. And then there are very, very close ties with discrete item factor analysis. So we had an episode a few years ago on that, and we can do a direct maximum likelihood. We can do a whole thing with polychorics, with weighted least squares, and getting an underlying continuum. Asymptotically, all of these things are honing in on the same thing. There's a really nice paper, actually by two guys who came through UNC, the lab here, R.J. Worth and Mike Edwards, have a psych methods paper in 2007 that really nicely compares and contrasts the IRT approach with the discrete item factor analytic approach and talks about directions for future research. So these things are intimately connected. The main thing is when you open the paper, does anybody open a paper anymore? When you look at your phone and there's some news story that says 8th grade students are still lagging behind expectations post-pandemic, right? We're seeing this stuff all the time. Dollar to donuts, that was an IRT analysis with an IRT scoring that brought those results to you. When you look at any kind of end of grade testing, when you talk about SAT scores, GRE scores, all of these things are governed by the item response theory model.
Did you say dollars to donuts?
I did. Is that not a thing?
Okay.
Boy, howdy.
There we go.
My favorite, my brother said this just over Christmas as he was telling me about how he fixed this thing in his car. And he was like, well, I did this. And then when I put the two together, they click together and Bob's your uncle.
Like, no, he did not say that.
Bob's your uncle?
I think if you say that, it is a very good discriminating item between whether or not you are old. If you say Bob's your uncle. So in the end, we wanted folks to be able to get some exposure to item response theory, to understand that it relates to lots of other things that you're already familiar with, to know that it's lurking out there in all kinds of scores that we encounter, whether it's in educational settings or clinical settings. And so it is something that we would put an NB next to. Do you ever use NB?
No.
Really? It stands for nota bene, which is to note well that something is very important. You never put an...
That sounds like something you'd say about your pasta. Did you enjoy your tortellini? It was nota bene.
Nota bene. All right. Well, to me, it's like the most pretentious of all the Latin. It's probably the liberal arts version of Q.E.D. If someone puts NB next to something.
Okay, see, I can see that. If it's a mic drop for liberal arts majors, there you go. So your challenge this week is at some point in a social setting is use the term nota bene and turn around and walk away. Report back next week. Take care, everybody.
Thanks a lot. Bye-bye.
Bye-bye. Thank you so much for listening. You can subscribe to Quantitude on Apple, Spotify, Google, or whatever identity-stealing platform you use, and please leave us a review. You can also follow us on Twitter X, we are at QuantitudePod, and check out our webpage at quantitudepod.org for searchable archives, playlists, show notes, a syllabus that organizes episodes under class topics, and other cool stuff. Finally, you can treat yourself to awesome Quantitude-themed merch at redbubble.com, where all proceeds from non-bootleg authorized products go to donors choose to support low-income schools. You have been listening to Quantitude, which is Latin for, seriously? 5 seasons? Quantitude has been brought to you by examples of other Latin phrases commonly used in academia and beyond. Quid pro quo, translated, this for that. A valuable term when negotiating with the dean for a new faculty line by mortgaging the same impending retirement for the 3rd time in 3 years. Alia iacta est, Translated, the die is cast. This is quite useful to mutter over your third glass of wine the day you've submitted your tenure portfolio. Acta non verba. Translated, deeds, not words. Keep this one in your back pocket for use in your next faculty meeting following a stirring speech from an otherwise absent colleague who is calling for greater departmental DEI efforts. Cogito ergo sum. Translated, I think, therefore I am. A little-known fact is this was the ultimate downfall of Descartes. After he walked into a bar and the bartender said, "Renee, can I get you a beer?" And he replied, "I think not." And he disappeared. Finally, illegitimi non carborundum, an admittedly false Latin term used extensively in the military during World War II, translated, don't let the bastards grind you down. Obviously, no example is needed for anyone working in academia. This is most definitely not NPR.